One more interesting effect, interference by thin films. This is caused by light's property of reflection, refraction, and interference. It occurs when you have light going through two media, and the refracted light then bounces off the other side, comes back, and interferes with the partially reflected light to produce wonderful colors. Here's a couple of examples. Soap bubble, and here we have oil on asphalt. Here's what we're talking about. We have a soap bubble here. This blue color is the soap bubble. It has an index of refraction of 1.33, and it is surrounded by air. So we have air up here, and we have air down here. Air has an index of refraction of 1. We have light. Let's say it's coming from the sun, coming this direction. Over here is an observer. That's kind of an eyeball right there. So what we have is some light bounces off the front surface, partially reflected, and comes over here so the observer can see it. Most of the light goes through the surface. You refract over here because you have a different index of refraction. It then partially reflects off this back surface, comes up, refracts one more time, and reaches the observer's eyes. It's these two rays here, the partially reflected light from the front surface and the partially reflected light from the second surface that will interfere with each other. What the observer sees will depend on the thickness of the film from here to here and the angle at which the light is observed. Since this is white light, all of the colors will be separated out, and the film thickness and the observation angle will also determine what colors are seen. That's similar to what we've discussed already with a prism and raindrops in a rainbow. Now if we have a very thin film, where instead of being this thick, maybe it's just like this, the rays coming from point A, which is the partial reflection off the front surface, and from point B, which is the partial reflection off the second surface, will travel almost the same distance because the two surfaces are so close to each other. But, and you don't have to worry about this right now, the ray reflecting from the front surface is inverted. So, since I have an inverted wave, so let's say that's coming like this, and then I have the ray that is not inverted but travels roughly the same distance, we're going to get destructive interference, and the observer will just see a dark fringe. He will not see any of the pretty colors from the colors separating out from the white light. The equations for thin film interference are determined using the same mathematical techniques that we use for the diffraction experiments. Now, in this case, we have two quite different equations here. We have T, right over here, which is the thickness of the film. And again, we have these orders, 0, plus or minus 1, plus or minus 2. And for constructive interference, which is where we'll see colors, we have the equation is 2 times n times the thickness divided by m plus 1/2, and n of course is the index of refraction. And destructive interference will result when the wavelength of light equals 2nt over m, and you'll get the dark fringes. A key thing to notice on this is the index of refraction here, which is 1, and here is 1. Both of them are less than the index of refraction of the material we're going through. Let's look at another case of thin film interference. So far we talked about where the index of refraction of the middle media, whether it's soap bubble or oil, is greater than the index of refraction of the media from where the light ray comes and where it goes. So let's see if I can fit a picture in here. We had the little soap bubble here. The index of refraction of light in air, the index of refraction of air for light is 1. So the light ray comes here. The soap bubble was 1.33, the index of refraction. And then it left there and hit another area where the index of refraction was 1. So now we're going to take a case where the index of refraction of a thin film, like an anti-glare coating on a pair of glasses, is greater than the incident light's media, but less than the index of the material on the bottom. So in that case, you would have like your coating here, and you might have an index of refraction here of air, which is n equals 1. The coating would have an index of refraction of 1.3, and then down here you'd actually have your eyeglasses, and that has an index of refraction typically of 1.5. So we're going to see what happens in this case. And the purpose of this is you want to maximize the transition of the light through the lens and minimize the reflection, or another word for that would be glare. The physics of this is slightly different. In this case, light will behave differently when it travels from a medium with a higher index of refraction to a medium with a lower index of refraction than it does when going from a lower N to a higher N medium. So the equations for this are changed as follows. Constructive interference this time is 2nt over m, where t is the thickness of that middle medium again, m is your order, and then destructive interference occurs over here. So in the one case we had the the soap bubble, your soap, and then we had the oil on the asphalt. And then over on this side we have an eyeglass and we have an anti-glare coating. So the equations are different between these two because of the varying indices of refraction. Here's what happened when we put a lens coating on a pair of glasses. The top part here doesn't have the anti-glare coating, and you can see the reflection of the person looking down on the glasses. This one has the anti-glare coating, so most of the light is transmitted through the lens and there's much less reflection, so you do not see the person there. Basically, this will help make photographs of people with glasses look better, and it enables you to see the person's eyes behind the glasses without that reflection.